You guys have been working through a lab on lots of different magnetic properties that involve both magnets and magnetic fields around current carrying wires. And in this activity, in this lesson, I'm going to go ahead and summarize some of those things so that you have all this information in one place. So let's just start with magnets and magnetism. Magnets have two poles, north and south, and unlike charge poles, we can't separate these, right? We can separate a positive charge from a negative charge, but a magnetic pole can't be isolated. If you have a north pole, a south pole is always going to be there. However, it does produce a field, much like electric charges produce a field. If you're trying to figure out which pole of a magnet is north or south, the north pole of a magnet will always point towards the geographic north pole of Earth if you suspend it, so it's allowed to rotate freely. That means, of course, that the North Pole of Earth, the geographic North Pole, is closer to the magnetic South Pole, since the opposite poles attract in a magnet, like poles repel. And as I mentioned, the magnetic field is actually, magnetism is a field force, so it energizes a region of space around it. That region is called a field, much like an electric field. But unlike an electric field, this actually is always going to emanate in one spot and then come back in another, because like I said, north and south always appear together. So in a permanent magnet, you're going to have the field lines coming out of the north side and then those trace around in to the south side. And you can always remember the direction of a magnetic field line. It's the direction the north side of a compass points if you put it next to the magnet. So if you put a north compass here, it's going to point away from the North Pole because the south is going to be attracted, the north is going to be repelled. And as you move it around, it's going to point towards the South Pole. So magnetic field lines point in the direction that a compass would point if you put it next to the magnet. If you put two magnets next to each other with like poles here, then the field lines are going to repel each other, much like charges. But if you put opposite poles together, then they're going to create a uniform field from one to the other. So the direction of the field is the direction of a compass. The strength of a magnetic field is actually measured in Teslas, and it's actually related to the density of these lines. So if there's more lines per unit area, then the field is stronger. And we measured the strength of a magnetic field line when we investigated the magnetic field produced by a current carrying wire. So if we take a look at that, now we're getting into the idea that magnetism and electricity are related, and we're actually going to tie that back together with these permanent magnets. We're going to see that electricity is actually related with them as well, or at least charge is related. So a current carrying wire produces a magnetic field, and you guys were able to measure this magnetic field at different distances from the wire, and you saw as you got farther from the wire, the magnetic field was weaker. Closer to the wire, it was stronger. Increasing the current in the wire produced a stronger field. And we synthesized all that information into this nice equation. So the magnitude of a magnetic field along a current carrying wire is given by B equals mu naught divided by 2 pi times I over R. Mu naught is a constant. It's 4 times 10 to the negative 7th Teslas times meters per amp. This number is defined like this because there's a law called Ampere's law that we're not going to get into, but if you define mu naught like this, then it actually makes Ampere's law a nice and pretty equation. For us, it makes this one a mess, but that's alright. So a current carrying wire produces a magnetic field, and we know the strength of that magnetic field, a distance r from the wire that's carrying a current I, from this equation. Mu naught is this constant. It's called the permeability of free space. Permeability refers to how well an object or matter supports the formation of a magnetic field. If it's got a higher magnetic permeability, it supports a stronger magnetic field. If it's got a lower, then a weaker magnetic field. Air, or a vacuum, is fairly low. Iron is about, I think, 5,000 times more than that of air. I'd have to look it up to know for sure, but the magnetic permeability of iron is much higher. It supports a very much stronger magnetic field. This equation is pretty simple, but it only gives you the magnitude of the field. It does not give you the direction of the magnetic field. And there's several right-hand rules that we use in order to figure out the directions of things. So the direction of a magnetic field along a current carrying wire is given by what I'm calling right-hand rule 1. That's what RHR-1 is. And for right-hand rule 1, what you do is you take your thumb, you point it in the direction of the current in the wire. Remember, current flows from positive to negative. Conventional current goes positive to negative. Even though electrons are actually flowing the other way, we go from positive to negative. So point your thumb in the direction of conventional current, and then your fingers will curl in the direction of the field. Of course, you're using your right hand for this. That means for a current carrying wire, if the current is up, then you're going to get circles of magnetic fields that are around this thing, and they're going to circle around the back. And since your fingers are going to curl this way, the magnetic field is actually, if you look into the top-down view of this, you would have a counterclockwise magnetic field. And if I was going to draw a top-down view, I'm going to use a vector that says, okay, here's the wire coming straight out of the field, out of the page. I put this little point on it, and that point tells me, oh, this is like an arrowhead coming out of the page. So the magnetic, or the wire, is coming straight up out of the page at me. Current is flowing up through that wire out of the page, and then my magnetic field is actually counterclockwise around it. Which means if I were to put a compass right here, it would actually point to the right. The north side of that compass would point to the right. Up here, the north side of that compass would point to the left. So the direction is given by the right-hand rule. The force is given by an equation. Now, if we take a current carrying wire and we put it in a magnetic field, then we're actually going to get a force on it, because this thing's creating its own magnetic field, and then we put it in a magnetic field, we're going to get a force. And that's what this is. A current carrying wire running perpendicular to a magnetic field is subjected to a force. If it's not perpendicular to the magnetic field, it's still subjected to a force, but we include then in angle. So if we have a magnetic field that is running to the right like this, then we want our wire to be perpendicular to that, our current carrying wire to be like this. Okay? And the current could flow either direction there, it doesn't matter. But if our current carrying wire is actually flowing like this, then it's actually not going to be subjected to a magnetic force, because those two things are parallel with each other. And if the angle between those changes, then we get more or less force. And that's actually what this equation shows us. The force on the current carrying wire is given by ILB, where I is the current in the wire, L is the length of the wire actually in the magnetic field, so over here that's this length, and B is the strength of the magnetic field measured in Teslas. If this is not perpendicular, then we actually include the sign of the angle between the magnetic field and the wire. So at this angle, when they're perpendicular, that's 90, and the sign of 90 is 1. However, if it's parallel, then the angle is 0, and the sign of 0 is 0, which of course means no force. So this is the maximum force when these two things are perpendicular. If it's anywhere in between, then you just tack on this sign theta to get the force. Again, this is the magnitude of the force. It's not giving us the direction. To get the direction, we need right-hand rule number 2, and right-hand rule number 2 is a little bit more complicated because it's actually got to deal with 3 things instead of 2, but we can still do it. First, you're going to take your fingers of your right hand and point them in the direction of the current. So for this picture I have up here, current is this red wire, it's pointing up. So I'm going to take my right hand and point my fingers up. Then I've got to orient my hand so that I can bend my fingers in the direction of the magnetic field, which is going to mean for me I'm going to orient my hand so my thumb is actually pointing down. I started with my hand straight, and then I have my fingers pointing up in the direction of that current carrying wire, and then I curl my fingers to the right in the direction of the magnetic field, which actually means my thumb is pointing down, which means the force acting on this wire is actually straight into the page. So if I was going to draw my force arrow, my force vector, I would have to draw it acting right here, and I would draw this X through it so that I know that that's the arrow going in. That's the tail of the arrow with the feathers on it, right? That's going into the page. So my force is in. So I have all these things at right angles to each other. So right hand rule number 2, fingers in the direction of the current, curl in the direction of the magnetic field, and then your thumb points in the direction of the force on the wire. Now this leads us to the idea that we don't have to have a wire, we just need to have moving charge. And in the equation F equals ILB, the one we were just looking at, I is current measured in amps, which is charge per second, coulombs per second. L is the length of the wire in the magnetic field, and B is the strength of the magnetic field. If we remove the wire and all we deal with is charge, then we're going to replace I with charge, which is Q. It has to move a distance in a given amount of time, which is velocity V, and it's still in this magnetic field, which is B. So we have this similar equation that says for a charge moving through a magnetic field, the force on the charge is given by Q times V times B, where Q is the charge, V is the velocity of the charge, and again, B is the magnetic field strength. This needs to be measured in Teslas, velocity in meters per second, and charge in coulombs. Now, just like before, the direction of the force depends on the direction of the magnetic field, and it depends on the direction of the velocity of those charges. That's a vector. And again, there is a sine theta here if the velocity is not, if the velocity of the charge is not perpendicular to the magnetic field. But it's the same right-hand rule for positive charge. You put your fingers in the direction of the velocity of the positive charge, curl them in the direction of the magnetic field, and then the force on a positive charge is the direction your thumb points. If it's a negative charge, same rule, except the force is going to be opposite the direction your thumb points, which would actually be like a left-hand rule, but we're not going to do that. We're just going to say in the opposite direction. Okay. I do want you to notice that both of these equations depend on charge moving. We have to have a velocity here, we have to have a current in the other one. If the charge is not moving, then there is no force exerted on the charge. So a magnetic field exerts a force on a moving charged particle. If the charged particle is not moving, then there's no force exerted on it. Then we did a lab where we said, well, let's take and stack up a whole bunch of wires next to each other and see what we get. And we got a magnet, and we were able to measure that as we increase the current in that coil of wire, we got a stronger magnetic field. And if we reverse the direction of the current, then we reverse the direction of the magnetic field. This is actually the basis of an electromagnet. That curling loops of wire, that's called a solenoid, and if we just take a solenoid, we actually create an electromagnet when we pass a current through it. And the reason for that is all those coils, if you look at any instantaneous or any single spot on it, it acts like a short straight wire, and it's going to create a magnetic field around it. So if this is the wire headed into the page, and then there's another wire at the bottom where this loop comes out of the page, then what we have is a magnetic field around this thing, and the magnetic field down here will be the other way around this thing. And then so inside we're going to get this nice uniform magnetic field, and outside we're going to get a uniform magnetic field the other direction. And this actually looks a heck of a lot like a bar magnet. So a solenoid actually has a magnetic field that's very similar to a magnetic field of a bar magnet, and we can actually calculate the strength of the magnetic field inside the solenoid by the equation B equals mu naught. This is the same thing, same constant we had before, times I, the current passing through the coils, times N, the number of the coils, divided by the length of the solenoid. So this lets us find the strength of a magnetic field of an electromagnet or a solenoid. And you can actually increase the strength of an electromagnet by throwing a piece of iron in there. And lots of different metals will work. Iron works really well, and that's because iron, being a magnetic piece of material, actually increases the magnetic field because of it's got that such a greater magnetic permeability. It supports the creation of a magnetic field much better than just air or a vacuum. Again, this is the strength of the magnetic field. It's not the direction, and so we have right-hand rule number 3 to give us the direction of a magnetic field. Although you can use right-hand rule number 1 as well if you just take an individual coil and try to figure this out. But it's easy. If you curl your fingers in the direction of the current, then your thumb points in the direction of the field on a solenoid. And then we get into actually getting things done with magnetism and electricity. So motors rely on this. There's a tool called a galvanometer, which measures current or voltage or however you set it up. But they all depend on the same thing. You have a magnetic field, which is usually created by a couple permanent magnets. So you'll have a magnet on one side. This would, of course, be the north side of a magnet, and it will have a south on the other side. Or this could be a horseshoe magnet that bends around, and you have the south pole of that magnet over here. So we have this nice uniform magnetic field from the pole of one magnet to the other pole, and this is the same picture for from several different vantage points or different points in time. And so what I have here is the face view. If you're looking at this on the front, you have this current carrying wire right here that has sections of it that pass through this magnetic field. Now this side over here I gave length A, and I gave this width B, and this whole thing is on this fixed axis in this magnetic field, so it can actually rotate around that. And this is the top view of the same thing. So this magnetic field is actually two-dimensional, and this current carrying loop is right here. This is side A, this is side B, we're looking down on it, and then its axis is here. So we've switched from a face view to a top view. And this one, it's been rotated a little bit. We'll get to that. Now, if we actually want to know about the force exerted on these wires, well, this wire, the top of it, there's no force exerted on it because it's parallel to the magnetic field. Same with the bottom section of the loop. No force exerted on it because it's parallel to the magnetic field. But this side over here and this side over here, they both have a force exerted on them. And they actually have forces in opposite direction, right? Because over here the current is flowing up, and on the right side the current is flowing down. And so using your right hand rule, if you take your fingers and curl them in the direction, or point them in the direction of the current, and then curl them in the direction of the magnetic field, you can see that the forces are going to be in opposite directions on either side of that. And over here on the right, this force is actually going to be out of the page, and on the left the force will be into the page, which is going to cause a net rotation like this. So this thing used to be here and it got rotated around like this. And as that happens, that's actually going to change the torque, but I'm a little bit ahead of myself. So we start with this thing perpendicular to the field, just like that, or parallel to the field. These are running perpendicular, but the angle between the face of this loop and the magnetic field is 0. So the face is parallel to the field. Now, that means these two forces are actually causing torques. And remember, torque is force times lever arm, as long as the force and the lever arm are perpendicular to each other. And so torque is force times lever arm, and since there's two forces that are both trying to cause the same rotation, we have to add up both torques to get the net torque. Well, the lever arm is half of this distance, right? The whole distance is B, half of the distance is B over 2. The force is given by I times B times this length of wire, which I'm calling A. It's the length of the piece of wire that's perpendicular to the magnetic field. And so what I get is the force is equal to I times A times B, where B is magnetic field, A is the length of the wire, I is the current, but I have two of those, each one exerting a torque with a lever arm of B over 2. So the torque that we get is I times A times B times B over 2, which means the net torque is actually twice that, because there's two sides to this thing, which means my B over 2 becomes B, and that means, if I redraw this loop of wire up here, I missed a little bit, this thing is A units tall and B units wide, which means A times B just found me the area of that loop. And so the torque on a loop of wire in a magnetic field is given by the current moving through the loop times the area of the loop times the strength of the magnetic field. And if you were to have multiple loops in there, multiple turns, then you would need to multiply this by the number of turns, because each one is going to have that force acting on it. So you can say N times A times B. Now, this actually explains how a direct current motor works. A direct current motor has magnets on the sides, and then you put current through this loop in the middle. And as that happens, this loop is going to be pushed around in a circle. Now the problem is, as soon as it gets to the top of this circle, the net torque on it is going to be zero, because that force is still straight up, this force is straight down, and that's not causing a torque. But its angular momentum will carry it past that. So it will keep spinning, but then we're presented with another problem, because now this side is going to be interchanged with that side, which means the currents are in opposite directions, which means the forces are in opposite directions, which means this thing is going to instantly want to start spinning back the other direction. We get around that by using a thing called a commutator and a brush. And so a commutator, it commutes the current the other direction. So you have a ring that's actually split, and it's connected up to the wire loop, one to each side. And so the wire loop connects this commutator. The brush comes in here and here. The brushes are fixed to a power supply, and the brushes don't move, but the commutator spins with the wire loop. So as this commutator spins, these are going to reverse which brushes they hit, and that's going to reverse the flow of current through the loop, and so the DC motor continues spinning in the same direction. So nice straightforward solution to making a DC motor always spin in the same direction. And in real life, you're going to have DC motors that are quite a bit more complicated, because they're going to have wire loops in multiple positions to keep the torque fairly constant, which means this commutator is going to have multiple splits in it instead of just one. But same principle, just on solving that problem of having the dead spot where there's no torque, and dealing with multiple commutators or multiple notches in my commutator for all those individual loops of wire. Now, as promised, I said that even permanent magnets have this property of magnetism because of charge, because we have charge that actually moves. And so there's this property called ferromagnetism, which is the property of permanent magnets. So a magnet that's a permanent magnet is called ferromagnetic. Ferro referring to iron. Iron is the most common permanent magnet. There's a couple other materials that can be magnetic at room temperature. Cobalt, I believe, is one of them. Nickel maybe as well. Those are ferromagnetic, and all ferromagnetic materials have something in common. They have little pieces in them called domains that act like tiny little magnets. Well, where do those come from? Well, it's actually the movement of charge, right? We've seen that current carrying wires create magnetic fields, and solenoids have these magnetic fields, but as soon as we turn the current off, the magnetic field goes away. As soon as we stop the flow of electrons, that magnetic field goes away. Well, in a permanent magnet, what it's actually due to is the electrons themselves that make up matter. So we tend to think of electrons as orbiting the nucleus, which is roughly alright, and they orbit in orbitals, and an orbital contains 2 electrons. But not only are they in orbitals, they also have spin. Now, spin is a quantum mechanical effect, but we're going to think about it as like the electron spinning on its axis. And electrons can have positive or negative spin, or up spin or down spin, but if you have 2 electrons in the same orbital, they spin in opposite directions. And that means they're going to cancel out any magnetic field they would have. So all materials are actually somewhat responsive to magnetic fields, because all materials are made up of protons, neutrons, and electrons, and these electrons have spin. Most materials are diamagnetic or paramagnetic. Diamagnetic meaning that the spin of the electrons it affects them in such a way that the field that it generates will actually repel the external magnetic field. Paramagnetic means it will be attracted to that external magnetic field, and ferromagnetic actually means that it can become its own permanent magnet. So, like I said, there's these regions in these ferromagnetic materials called domains. So if I had a chunk of iron, then every little piece of this iron you can think of, if you split it up into these just random little jagged chunks, these are domains, and within this domain, the atoms have aligned themselves in such a way, or the electrons, that they all have spin, a parallel spin, which means each one of these domains acts like a tiny little magnet. But those domains are randomly oriented in space in that iron chunk, so that means they're not going to actually create a net magnetic field. They're basically, all that randomness is going to lead to no magnet. However, the cool thing about this is if I apply a strong external magnetic field, then it's going to cause all those domains to align with that magnetic field, which means instead of randomness in here, I have a nice uniform magnetic field in my chunk of iron. And it stays that way even after I remove the external magnetic field. So now I've taken this piece of iron and I've made it a permanent magnet by placing it inside this strong magnetic field. Now, I can misalign those domains again. We can demagnetize this thing if we get all those domains in random order. And there's a couple ways to do that. You can strike it really, really hard on something, and that can cause enough random motion to jar some of those domains. But you can also heat it up, right? Heating something up causes those atoms to start vibrating more and getting more random motion. And if I heat it up enough, I'm never going to be able to make it a magnet. And the temperature at which something will not be a magnet at all is called the Curie temperature. And for iron, the Curie temperature is fairly high. It's around 1043 Kelvin. So you got to get it hot. But for some of the other permanent magnets, like rare earth magnets, neodymium magnets, they actually have a lower Curie temperature. They're a much stronger magnet, but they're a much lower Curie temperature, which means in some applications they don't work as well because that high temperature is exposed and can actually cause their magnetic properties to go away due to the random motion of the particles.